Okay, take a look up here. So I did a couple things on number one. I showed the formula off to the left-hand side. So the formula, if you're doing a conditional probability, this is the condition. So baseball already happened. That effectively reduces the sample size. So we do, for the formula, it would be the probability that junior intersects baseball. That's going to be this one right here, 34 out of 300. I've written it right here. Divided by the probability of baseball. So baseball is 68 out of 300. So I did 34 over 300 divided by 68 over 300. You can skip right to here because if we're given baseball, if that's the condition, it limits it to this sample space right here. It's only those 64 people total, and 34 of them are juniors. So you can skip right to here to 34 out of 68, which reduces to 1/2. Okay, if you want to use the formula, which I would know, it works really well for more complicated situations. If we're going to do the probability of soccer given senior, then all we're looking at is just this. We've effectively reduced the sample size from 300 students to just those 150 students, and we want soccer for those seniors, right? So that's going to be 44 over 150, and we just reduce that. So let's see, 4 goes into both of those. Nope, 2 goes in there, so that'd be 22 over 75, and then we could change that into a decimal if we wanted to. Okay, any questions? All right. So we're going to talk about compound events today. We've actually done a couple of them. We didn't call them that, but here's what a compound event is. It's more than one simple event strung together. So we've got 2 simple events or 3 simple events strung together. So if we have something like tossing a coin, that's a simple event. But if we toss a coin repeatedly and record the results, or throw another simple event in there, like rolling a die or something, then that's called a compound event. And we usually indicate those with intersections. Okay, and as long as they're independent, then we can use the multiplication rule in order to compute the probabilities. So here's what it looks like. If they're independent, then it's the probability of A intersect B is the probability of A times the probability of B. So we literally just multiply them together as long as they're independent. And like it says on this line right here, you can extend that to 3 events or 4 events, as many events as you want. You can string those together. And a tree diagram, which they actually start introducing in 7th grade, is a good way to keep track of compound events. Since you guys didn't take 7th grade math, we're going to show you one right now. So this is an example of a compound event. So this is just flipping 3 different coins and then recording the results. So we would start right here, and then what can happen is we can either get a head or a tail. They both have a 1/2 probability. If we get a head, then we flip another coin. We can get a head or a tail. Each one has a 1/2 probability. For each one of those, we flip another coin. Each one has a 1/2 probability. So here are the outcomes. So when you take the practice test and when you take the test, you're going to need to be able to list these. So here's what happens. We can have a head, then a head, then a head. A head, head, then a tail. A head, a tail, and then a head. So head, tail, head. And you'll notice that the first branch of each one of these is a head, and then this one is going to be a tail, then a tail. So notice how we've got head, 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 tail, tail, head, and then tail, tail. The bottom of this list is basically going to look the same because we've got tail, head, head, tail, tail, head, tail. And this one's going to be tail, tail, then a head, and then the very last one would be tail, tail, tail.
So it's opposites.
So if we were going to find the probability that we get a head and a head and a head, it's going to be the probability of a head because each one of those are independent, times the probability of a head, times the probability of a head. So 1/2 times 1/2 times 1/2. We're basically just following this branch all the way up. So 1/2 times 1/2 times 1/2 is 1/8. So if it's tail, head, head, tail, head, head, that's this one right here. It's going to be 1/2 times 1/2 times 1/2. So we end up with 1/8 again. Everybody good there? Okay, now, there are 8 possible outcomes. We listed them. And when you're asked to do a diagram on the practice test or the test, this is what a tree diagram would look like. We've got the probabilities there, but there's another way that you can figure it out. If these are all independent and it's a fair coin, these should all be equally likely. So every one of those events should have a probability of 1/8. Because they're all equally likely. There are 8 outcomes. And if you want the first one, triple head, that's the very first one, 1 out of 8. All of those would have the same probability. And keep this in mind, this is going to come up again. If you add all 8 of those probabilities together, 1/8 plus 1/8 plus 1/8, altogether we're going to get 1 for the total probability. So take a look at the next one. This is different. This is kind of a contrived compound event. So it says fill in the missing probabilities on the tree diagram, and here's the compound event. Flipping a coin and rolling a die. So fair coin, fair die. This is going to be 1/2 and 1/2. When we roll the die, the probability of getting a 1 is a 1/6. So what is it for not a 1? 5/6. It's got to be the rest of that probability. So it's got to be 5/6. So we're going to have 1/6 and 5/6 on each one of these. So probability that you get a head, intersect with a tail. Probability of a head is 1/2. Probability of a head intersect with 1. Sorry, I think I said that wrong. That would be, times 1/6. So that would be 1/12. Probability you get a tail intersected, so and, not a 1. So probability of a tail is 1/2. Probability of not a 1 is 5/6. So we end up with, 5/12. Everybody good there?
That's a lot more than 1/12.
Okay. So this is another way to do that same tree diagram. Okay, that's a very specific way over there if you break it up with 1 and not 1. This takes longer to list, but if we went through and listed this, this would be a head and a 1. This would be a head and a 2. This would be a head and a 3, and so forth, all the way down to a tail and a 5 and a tail and a 6. Since this diagram is just like the other one, these are independent and they're equally likely, there are 12 outcomes, and we could actually figure that out without multiplying probabilities. We could just look at the sample space and the desired outcome. So a head and a 1 is this one out of all 12 of them. A tail and not 1 is all of these guys right here. So it's 5 out of the 12, and that's a lot quicker way to do it, but you do have to have the diagram or at least visualize the tree diagram. Okay, any questions about tree diagrams or finding probabilities from those? Okay, let's talk about the fundamental counting principle. So here's the fundamental counting principle. These tree diagrams work really well if you've got a small number of simple events, and those simple events don't have many outcomes. So you can see even just throwing a die in there makes this much bigger than having the coins. So if we've got a lot of simple events, or we've got some simple events with tons of outcomes, like if we had a 12-sided die or something like that, it makes it more complicated, and that's where the fundamental counting principle comes in. So if a compound event is a sequence of events in which there are, P outcomes for the first event, Q outcomes for the second event, and R outcomes for the third event, and so on. You can just keep assigning variables for each one of those. Then there are P times Q times R times however many you've got multiplied together. That's how many outcomes there are in the sample space. So we just multiply them together, whatever those choices happen to be. So flip the page over and take a look at example 3. So we can use the fundamental counting principle to figure out how many outcomes there are in the sample space and how many outcomes there are in our desired event, and then compute the probabilities based off that. So an organization has member ID cards that consist of 2 letters followed by 3 digits. So what I like to do in situations like this is, let's write down how many choices have to be made. Okay, we've got to select 5 different parts of this ID card, and the first 2 are letters. They didn't say we couldn't repeat or anything like that, so there are 26 choices for the first one, 26 choices for the next one, because they're both letters. And Jack, how many choices for the digits? Oh, he wasn't paying attention.
Oh, Jack.
Okay? 10 choices for each one of those, because 0 through 9 we've got 10. So if you multiply those together, grab your calculator unless you've got 26 times 26 memorized.
I
Anybody got
wasn't
that?
listening either.
It is 676.
676000.
Very good. So there are 676,000 different ID badges or ID cards possible.
What?
Sheesh.
Okay.
What's the probability?
What's the probability that we randomly select one of those ID cards and it's IM747?
1 in 600.
1 out of that many.
Yeah, because we're choosing it this way, and this will come up again in a minute. There's only one I, there's only one M, there's only one 7, there's only one 4, and there's only one 7. Okay? So we multiply those together, we get 1 out of that many. If you wanted to, you could do this though. So everybody agree that's the answer?
Yes, I think so.
For each one of these, if you wanted to say what the probability was and then multiply them together, this is 1 out of 26, 1 out of 26, 1 out of 10, 1 out of 10, and then you can multiply them together. You still get exactly the same answer using the multiplication rule. Okay, everybody got that?
Yeah.
Okay, would you look at example 4, and would you figure out we've got a 1 through 8 spinner, we've got a die, and we've got a coin. How many outcomes are possible? Don't say anything, figure it out. Crew, what have you got? Oh, crew.
Probably like 136.
Okay. Caleb, how many outcomes are there on the spinner?
8.
8.
Oh,
Okay,
yeah,
Zach, how many
just
outcomes on the
spinner.
die?
6.
6. Okay, Dane, how many outcomes on the coin?
2.
2. If you multiply those all together, you get 96. There are 96
That's pretty
outcomes
close.
altogether. Imagine if you had to make a tree diagram for that one or the ID cards. That would be a huge pain. Way easier to count this way. So now, without saying anything, careful, probability that you randomly select 4 or more, 2 or less, and a tail. Just part of this at a time. Side. How many are 4 or more? 5. Luke, 2 or less? 2. And D. Tails? 1. So if you multiply those together, you get 10. So you get 10 out of 96, which, let's see, so that's going to be 5 out of 48.
Yep.
And can't reduce that. If you wanted to, you could say 5/8, 5/8, 2/6, 1/2, and then do some reducing from there. You still get 5/48. Okay, are there any questions? We're all right?
Oh, this is just a really dumb one.
Sure.
Can you cross cancel the 2 and the 2?
Sure you could. Yep.
And then you
So
just
there's your 5/48s right there.
Yeah.
Yep. Okay, so let's talk about dependent events. We've calculated these before, but we haven't talked specifically about a rule. You can't use the multiplication rule because that multiplication rule only works with independent events, but we can modify just a little bit. So if they're dependent events, if we've got A and B and they're dependent, the probability of both of them happening at the same time is the probability of A times the probability of B, but we've changed something about this. It's the probability that B happens given that A has already happened. So what I want you to notice here is this is just like the multiplication rule was before, but we changed this and we say it's the probability of B given that A has already happened. So notice that they change order. It's not AB here, it's BA when we do that conditional probability. Okay? So we're going to slide down here. And just like we said before, you can have this for any number of events. It doesn't have to be 2 events, 3 events, and so forth. So here's what we've got. There are 7 dimes and 9 quarters in a wallet. Suppose 2 coins are selected at random, one at a time, without replacing the first one. So this is the probability of a quarter and then a dime. So There are 16 coins altogether. So the probability of randomly selecting a quarter is 9 out of 16. Don't say anything. Probability of selecting a dime. 7 out of 15. Very good,
That's what I
because
was
we
gonna
didn't
say.
replace it. So that's going to be 7 out of 15. So we can do a little bit of cross canceling. That's going to be a 3. That's going to be a 5. Correct me if I'm wrong.
Oh, yeah.
21 over 80. Is that all right?
Is that the answer?
Mm-hmm.
Okay, so I don't have to do it the other way.
Nope. Okay. Probability you get a dime, and a dime. Okay, on the bottom there's 16, then 15, and then 14, right? Just that fundamental counting principle. On the top there are 7 dimes to start with the first time. 6, then 5. Can do a little bit of cross canceling. So I get a 2 here, I get a 3 here, I get a 3 here, and I get an 8 here. I can cancel the 2 of those, so correct me if I'm wrong. 1 out of 16? Did I do the arithmetic right? I see some thumbs up. Everybody good there? Okay, next one. A basket contains 2 apples, 6 peaches, and 5 oranges, and 3 fruits are randomly selected in sequence. So you take them one after the other.
Is that the same thing?
N equals
as
13 on
like
this
the
one, right?
last one?
Yep. Yeah, so we're not replacing them and drawing them again, we're just grabbing them. Okay, would you figure out the probability of orange, orange, and peach?
Ah, love peaches. Favorite fruit.
That was not fun, Jack. Cause it banged.
Oh.
Answer or question?
Question. Are we assuming that the previous without replacing the first one still applies here?
Because we're drawing them in sequence.
You gotta like
5
line them
times
up
4
like.
times.
Okay, Abby, that first orange, how many oranges are there to choose from? 5. And how many fruits are there altogether? 13, yep. Okay, second orange, Keely.
5 or 4/12.
4/12, very good. And Megan, how about that peach?
6.
Out of 11, okay? And then you can do some simplification from there.
I
Okay.
got it. I have the answer.
You have it?
I have it.
What is it?
10 over 143.
10 over 143. Raise your hand if you got 10 over 143.
I did.
Excellent.
Me.
Okay, don't say anything out loud. Apple, apple, apple.
Wait a second.
Samara, how come?
There's not
Yeah,
enough
so
apple.
you could set it up all day long. This is still going to be 13. This is still going to be 12. This is going to be 11. There's 2, there's 1, and then there's
0. You
0.
can't
So the
multiply
fact you
with
can't get
0.
that third 0 negates the whole thing. Okay,
So should we write 0 or not possible?
What if we
so you would write, it says probability, so the probability is 0, which means it's impossible. Okay, last problem here, and then I've got a thought question for you. So it says, a cereal company conducts a blind taste test. 40% of those surveyed are kids, while 60% are adults. 75% of the kids like the cereal, while 90% of the adults like the cereal. What is the probability that a person selected at random is a kid who likes cereal? D, how do we set that up?
We take 4 over 10 for 40% of the kids.
Okay, so we're going to do the probability of a kid is 40%.
And then we would take the probability out of the 40%, we have to take 75% of that. Which
Mhm.
is about 30%.
Okay, so if you take a look at this, what I've done here is I've written down the probability that they like the cereal given that they're a kid. And what's that probability?
That's like 30%.
What's the probability that they like it given they're a kid? 75%. So we'd multiply the two of those together and we get, like he said, 30%. So this is going to be the probability that they're an adult, which is 60%.
Who likes?
And the probability that they're an adult who likes the cereal?
90.
90%, which if I multiply those together, I get 0.54.
Yeah.
So a kid, 40%, doesn't like the cereal. That's going to be, let's see,
25.
75. Its complement would be 25, so this is going to be 0.25. So this is going to be 0.10. And adult again, probability that they don't like the cereal if they're an adult is 10%, so you end up with 0.06. Now, any questions about that? Because I've got two thought questions here. Okay. Do you notice anything about all those added together? Luke?
They're 100, they're one, my bad. 100%.
Yeah, they're one. They're one. They represent 100%, which is what should happen because we've represented all the possibilities in the sample space. They're either a kid or adult, and they either like the cereal or they don't. There's nothing outside of that, so that's the entire sample space. It should add up to 1, okay? So it adds up to 1.0, so 100%. And, thought question right there, don't say anything. Would you figure out that probability right there? Okay. What number goes on the top? It kind of seems like it might be 4 because how many choices are there for the first one? 2. How many choices are there for the second one? 2. It seems like that ought to be the way it is. But the problem with that is this. Once you choose that first one, these are all 10s, but once you choose, oh, sorry, take that back. They're not 10s, they're 1s because we want 7, 4, 7, right? Once I choose, how many choices are there for the first one? It's either a U or an I, so that's a 2. Once you choose that first one, once this is an I, how many choices are there for this one right here? Once the first one's an I, what's the only one that's acceptable for the second one? An M, so there's only one of them. And once you choose a U, there's only one that's acceptable, and that's an R. So this is 2 out of that many right there. So if you multiply all those together, we get 2 out of that, which is 1 out of 300,000 or whatever.